On a real planet, it rains glass sideways at 7,000 kilometers per hour. Yes, sharp silicate shards actually fall there, driven by brutal winds. Bottom line today, this weather can kill you in seconds. We are looking at HD 189,733b, a nearby hot Jupiter. Hot Jupiters are gas giants parked scorchingly close to stars. That proximity superheats their skies and cooks strange clouds from rock. Those clouds seed raindrops that harden into glassy grains while falling. Then planet-wide winds whip the grains sideways like airborne sandblasters. Spectra reveal it, and the stakes are real. So the picture is simple. Glass rain plus hypersonic winds equals danger. Picture a cobalt blue world hanging near an orange dwarf star. Astronomers call it a hot Jupiter, a broiled gas giant. Understanding its weather stretches climate physics beyond Earth and sharpens models. It hugs its star so closely, a year lasts 2 days. That closeness locks one hemisphere in daylight and one in night. Starlight pounds the dayside near 1,000 degrees or higher. Gas expands there, while cooler gas contracts on the night side. The contrast builds colossal jets that circle the equator like rivers. The pressure difference drives global jets that race across the Terminator. Speeds reach around 2 kilometers per second, sustained. That is faster than rifle bullets and constant for years. Meanwhile, rock vapor condenses into silicate droplets within rising clouds. Its sky looks blue not from oceans but from fine haze. Tiny grains scatter shorter light like Earth's daytime atmosphere. That same haze seeds the violent rain we are chasing. Observers estimated its distance at 64 light-years from us. Its orbit sits around 3% of Earth's distance. The planet is slightly larger than Jupiter and twice as hot. Higher up, the air thins and temperature swings become steep. Lower down, chemistry favors silicates, iron, and exotic condensates. Cloud layers stack in bands, while storms spool along endless latitudes. So we are dealing with a broiling, wind-lashed gas giant nearby. Here is what glass rain actually means in plain words. Silicate is rock vapor that condenses into droplets, then hardens into glass. You should care because tiny glass falling fast becomes a lethal sandstorm. Cooling air lets silicate molecules cluster and form microscopic liquid beads. Those beads collide, grow, and freeze into amorphous glassy grains. Fresh grains become cloud nuclei, so more grains form around them. Rising plumes lift grains high, while gravity pulls them downward. Winds stretch the fall into long, slanted paths across the sky. Temperatures span about 1,000 to 2,000 degrees out there. Lower pressure shifts the glass transition and sets grain textures. Models predict grain sizes near 1/10 to 1 micron wide. That is roughly the size of smoke or volcanic ash. Example in real terms, a human hair is 70 microns across. A cloud packed with micron grains turns blue light aside very strongly. That scattering explains the blue tint and the hazy look. As grains rain, some sublimate back to vapor in warmer layers. Others survive the plunge and sweep sideways in the roaring wind. A rain shaft becomes shards, not droplets, slicing wherever the jets drive them. Grains can also clump briefly, then break apart under shear. The cycle repeats continuously, while the planet never cools at night. Observers see the signature as a steep blue spectral slope. Bottom line, glass here is chemistry, not a metaphorical nickname. Now think about the wind turning rain into razors midair. Supersonic here means faster than sound in hydrogen and helium. That speed is around 2 kilometers per second, give or take. The jets clock near 2 kilometers per second on average. Heat flows from day to night, and pressure gradients do work. Air accelerates along the equator and wraps momentum around the globe. Coriolis effects bend the flow and lock in banded jets. Falling grains feel gravity downward and hurricane force sideways at once. Their paths tilt hard, so raindrops become diagonal cutting streams. Tiny test, imagine grit stinging at 100 kilometers an hour. Now scale to thousands, with glass instead of dust and endless duration. Even a grain a few microns wide hits with fierce momentum. Billions of hits per square meter make surfaces erode like chalk. Larger clumps punch deeper, then shatter under shear into fresh shrapnel. The constant flux erodes suits, windows, and instruments rapidly. Net result, the weather is not just hostile, it is actively weaponized. How do we know any of this without flying a probe there? Starlight tells the story when the planet crosses or glows through space. During a transit, light filters through the limb of the atmosphere. Different molecules absorb different colors, leaving a barcode in the spectrum. A steep rise toward blue hints at tiny scattering grains aloft. Sodium lines show up shifted, revealing fast winds streaming eastward. On the day side, thermal glow waxes and wanes as the planet turns. Measuring that glow, each phase draws a heat map around the world. The hottest spot sits east of noon by several tens of degrees. That offset fits winds hauling heat away before it can re-radiate. Ground telescopes use Doppler tricks to track wind speeds directly. Shifts of a few kilometers per second match the jet predictions. Space telescopes like Hubble and Spitzer sketch the early picture. Newer arrays sharpen the lines and test grain sizes more carefully. Rule of thumb: the smoother the slope, the smaller the grains. Observers stack many orbits because signals are faint and noisy, yet patterns repeat cleanly and point to robust weather features. Researchers also compare many hot Jupiters and see the same trends. That crosscheck raises our confidence and constrains the storm physics tightly. So the evidence ties spectra, winds, and heat maps to glassy clouds. Glass is not the only deadly rain falling in alien skies. Some worlds rain iron on the night side after dayside metal vaporizes. WASP 76b is the poster child for that scene. Ultraviolet light bakes the dayside above 2,400 degrees. Metals turn gaseous there and hitch rides on the screaming winds. As air reaches the cooler night side, iron condenses into molten droplets. Those droplets fall like metallic drizzle and likely evaporate near dawn. Spectrographs caught neutral iron where it should not persist in daylight. The lines also skew, hinting at winds hauling metals across the terminator. Scientists even inferred asymmetries, consistent with night-side condensation into heavy rain. Kepler-13 Ob likely snows corundum, the mineral that makes rubies. Ultra-hot conditions forge aluminum oxide clouds and sprinkle crystals into darkness. Imagine umbrella bones glowing red, then melting under an alien storm. The chemistry flips with temperature, and the weather flips the world. Numbers vary between planets, but the pattern keeps showing up. Under such storms, umbrellas are geology experiments, not shelter. Bottom line, exotic rain is a real forecast, not science fiction. Back home, Venus often gets called the planet of acid rain. That phrase is true aloft, yet misleading near the ground. Clouds brim with sulfuric acid droplets born from volcanic outgassing chemistry. Sunlight drives reactions that stitch sulfur and oxygen into aggressive acids. Those droplets do coalesce and fall within the cloud decks, but the air grows scorching hot below, near 500 degrees. Falling acid warms, then boils off before it reaches the surface. Raindrops vanish around 25 kilometers up, leaving a baking haze. So the ground stays dry, while the sky eats metal and stone. Landers survived minutes to hours as the air stripped their insulation. Sensors corroded and electronics failed under that crushing, toxic blanket. The hazard there is gas and heat, rather than slashing precipitation. Meanwhile, Titan rains methane gently under a cold, oxygen-starved sky. That rain is flammable to us, but cannot burn without oxidizer. Same lesson repeats. Context decides whether alien rain can kill. So Venus teaches nuance, while hot Jupiters teach brute force violence. What would it take to survive one glass storm for an hour? First, define the threat clearly, not poetically, to guide design. You face micron glass shards at hypersonic speed in hydrogen. Pressure is near 1 bar, but temperatures are scorching hot. High temperature weakens many plastics and embrittles some metals over time. Ceramic armor helps, yet ceramics crack under repeated high-velocity hits. Spacecraft use Whipple shields with layers that shred incoming fragments. That concept could work if layers could self-heal under abrasion. A sacrificial outer skin would ablate and carry heat away. Behind it, foam and cloth would catch slowed grains effectively. Windows would need thick-fused silica with constantly repolished outer faces. Actuators and seals would hide behind baffles far from the airstream. A backpack cooler would dump heat into radiant fins rapidly. Fluxes can reach billions of grains per square meter each second. At 2 kilometers per second, abrasion becomes catastrophic very fast. Even tungsten plates would erode fast while sensors go blind. Bottom line, a cautious robot might last, a person probably would not. That blue world with sideways glass rain is not a metaphor. It is a nearby gas giant where weather turns rock into knives. We read its storms from starlight, and the numbers hold steady. If that first line grabbed you, the payoff is now clear. On some planets, rain alone can kill you, quickly and quietly. I love chasing these strange forecasts because they change how Earth feels. If you want more cosmic weather, join me for the next one. Thanks for hanging out, and keep your visor down out there.